Wanted to do privacy preserving multi-party computation using trusted hardware? As it turns out, I haven't, but we are very fortunate to have Derek here for those of you that have. Derek Miller works at ARM and has been focusing on practical cryptography and confidential computation. Today, Derek is telling us about the Veracruz project, which is a software stack providing safe, neutral ground on untrusted hardware that allows untrusted parties to collaborate on computation. Now, we're quite likely to have time for questions after Derek's presentation, so please put your questions into the question tab on Venulus, and our moderators will pass them over to me for afterwards. Derek, take it away.
Thank you, Jeff. So thank you for the introduction. I don't need to do this slide at all. First thing I'm going to start with is who the Veracruz team is. We're all employees at ARM. We've got Basma El Gabouri in the UK, Chris Haster in the United States, myself also in the United States, Dominic Mulligan in the UK, Nick Spinelli in the UK, Hugo Vincent, who is actually a Kiwi living in the UK, and Shales Young, also in the UK. So I'll go on next to what Veracruz is. And to do that, first I need to start with some definitions that you may or may not be familiar with, but it's good to set some a baseline. First, we've got remote attestation, which is, there's a lot of different terms going around there, but it's essentially a way to establish trust in the state and identity of a remote computing environment. Usually used by you're probably most familiar with it as TPMs, which was the previous talk. It's usually based on, it's always based on previously established trust relationship, which could be the owner of the manufacturer of the computer or that computing environment. The second term is a trusted execution environment, which is sometimes referred to as a TEE. It's an isolated computational enclave inside a larger computational environment. It provides confidentiality of data from the larger computation environment, which may or may not be trusted. And examples of this include Intel SGX, which is we're one of the big ones out there. There's ARM Trustzone, has slightly or actually quite a bit different trust properties. And then as launched in, I believe it was October of last year, the AWS Nitro enclaves. So for the background of where Veracruz came from, it began, actually, it was my colleague Dominic Mulligan's idea that he believes that the isolation provided by trusted execution environments and remote attestation allows for the design of novel applications with fine-grained access control. It allows computations to be safely moved around without sacrificing privacy or integrity, and it potentially can separate possession of data from control over that data. So in here, the strong isolation is our term for a range of hardware and actually firmware-based isolation mechanisms aiming to provide privacy and integrity guarantees. So Veracruz started as a research project within ARM, and it's our vehicle for understanding what these technologies are capable of and what a computing ecosystem utilizing them would look like. So the Veracruz framework that we've developed and are still developing is it's a framework for defining flexible and efficient multi-party computations. It aims to support common use cases that are usually used for advanced cryptographic techniques. You may or may not be familiar with these terms. For example, homomorphic encryption, which is the ability to compute on encrypted data without decrypting it. There's a whole spectrum of homomorphic encryption algorithms, going from partially homomorphic, which Microsoft actually just did a blog post on last week about how they're using it for password verification, not verification, but password. I don't remember the term. It's basically they're checking passwords against a list of bad passwords. The problem with homomorphic encryption, and especially when you get to fully homomorphic encryption, where you're able to do addition, subtraction, and multiplication, is that it's incredibly slow, and it also increases the size of the data exponentially. So so Veracruz, the goal here is to provide some of the same properties of homomorphic encryption, but to be efficient and fast enough to execute on interesting programs, just on programs themselves. Familiar, which would allows programmers that are to use familiar programming languages. It's general, seamlessly support a large class of multi-party computations, and reusable So basically, to be able to work across different platforms with different requirements. And in common with those techniques, we hope to provide the strong security and privacy guarantees. So practically speaking, when Veracruz has been open sourced provisionally, we're still trying to get the lawyers to all agree on the right terms with the Confidential Computing Consortium. And right here is the link on GitHub is the link to our source code. It's mostly written in Rust, and with some parts of it, unfortunately, still written in C. And of course, if you've ever worked in the Rust ecosystem, it's fairly difficult to get away from having some C in the dependencies. Our goal is to eventually remove those, but that's not where we are right now. And it utilizes trusted execution environments that are currently available on the market: Intel SGX, ARM Trustzone, and AWS Nitro enclaves. And also, to add to the buzzwords to maybe pique your interest, we use WebAssembly for the runtime environment. So from a view from approximately 50,000 feet of what Veracruz looks like, it starts with data coming from multiple parties. The data inputs, they can originate from different agents, they can be mutually distrusting, or they can all be colluding. It doesn't really matter. Additionally, we've got the program that is coming in. The program can also originate from a different party, and it's this program that we will be executing is WebAssembly. So on the target system, which we refer to as the host, inside there is a TEE where the Veracruz software is executing. Inside the TEE and authenticated as part of the entire handshaking process between the participants is a policy. It details the roles and the identities of everybody involved in the computation, and it describes who can retrieve the result. It also has it has some optional computational limiting features in there to allow the host to protect himself from denial of service attacks, somewhat at least. So the program and the data are provisioned securely using TLS, which is terminating inside the TEE. The TLS connection, this is really important, is terminated inside the TEE, not in the host. And then the TEE computes the result using the program on the data. And then the result retriever is able to retrieve the result. And one thing that's quite important here is to maintain secrecy. We need to control the expressivity of the program that we can run. This is another great feature of WebAssembly, which I'll get into in a little while. So first, before I get into the intricacies of the attestation process that we go through, I'm going to give a brief overview of the platforms and the various trade-offs for each of those platforms. Of course, we're going to start with ARM Trustzone, because you got the ARM all over the slides and on my shirt and even in my nice cup. So anyway, if you're not familiar with ARM's Trustzone environment, what you have here on the left is a diagram of what the software ecosystem looks like on a device. The light blue is considered the non-secure world. The dark blue is the secure world. Linux would be typically running in the rich OS on the light blue side. The hypervisor can be any hypervisor you want. Normal Linux applications or the light blue app blocks on the top. And on the right, we have another operating system and application stack, which is referred to as the trusted world. For the trusted OS on the secure side, we use Opti as that trusted OS. It's an open source operating system that is maintained by Linaro. And the Veracruz runtime, which was inside the TE on the previous block, is running as a trusted application on top of Opti. The untrusted pass-through, which we refer to internally as Sinaloa, but we're in the process of renaming everything because naming everything after states in Mexico got a little confusing sometimes. So the untrusted pass-through runs as an application on the Linux side and the rich operating system side. All of this is running on top of a QEMU virtual machine. And it uses, for the Rust development inside the enclave, we use the Rust Opti Trustzone SDK, which we have found to be well, not even surprisingly, it saved us a gigantic amount of time to be able to use a pre-existing framework. But the limitations on this Trustzone platform is that we're currently running on a virtual QEMU platform. That means we're running on software on top of software. The enclave is not protected by hardware. And we are currently limited to approximately 22 megabyte total of WebAssembly binary plus the data size. Since we're on a virtual environment, we could fix this problem, but if you have any experience looking at actual ARM Trustzone environments, 22 megabytes is quite large for most of those environments. So, upping it would just be less realistic than actually using real hardware. Also on Trustzone, the attestation is complicated. A typical Trustzone trust model is not quite appropriate for this use case. Trustzone typically works off of loading signed binaries of trusted applications. It's not worried about loading applications from user space. So the attestation, what we had to do on this platform, we did have to fake it, as it's not supported by the Trusted OS, opt-t, or the manufacturing provisioning process. I believe Microsoft Research has a fork of opt-t that does support attestation, but we're not using that at this point. So these limitations mean that the confidentiality and integrity guarantees do not apply on this platform. Our Trustzone environment is just a demonstration. Now on Intel SGX, some of the limitations is starts with we are working on SGX version 1.0, and it limits enclave size to 128 megabytes. That being said, 96 megabytes is the maximum usable that you have on SGX. SGX version 2.0 has lifted these limits, but we have been unable to acquire a system that supports it. Every time we find one, anybody that's selling one, we go out to buy it, and they drag us around the corner for a couple months, and we don't end up getting it. So on SGX, we use the Rust SGX SDK, which is an Apache project, but it was originally developed by Baidu. This environment was, as with the Trustzone environment, this was a great help in getting our systems up and running. Now, AWS Nitro enclaves. This is AWS's recently launched feature. It was launched in October. It's supported by the AWS Nitro hardware, which is custom hardware that Amazon has developed for their data centers. There are virtually no memory restrictions on Nitro enclaves. The amount of memory you can have is only limited by the EC2 instance type that you're running on. It runs a stripped down Linux stack inside the enclave. They don't provide a lot of information on that at this point, but it is, which honestly, that's having Linux inside the TCB makes me a little nervous, but the ease of use is great on these. They use raw vSockets sockets for communication between the non-secure and the secure world. The enclave itself runs on a reserved CPU that's inaccessible to the non-enclave software. I believe the reason they do this is to protect from certain side channels. It doesn't protect from all side channels. That feature doesn't protect from all side channels, but it does make things a little harder on that side. Only one enclave is allowed per EC2 instance, which got quite annoying for me. That being said, I understand why they do it. They do say that maybe they'll do it and support it in the future. And the other part about AWS Nitro enclaves is the nature of trust. When I want to use SGX on a system that's not owned by me, it often comes down to the fact that I don't trust the owner of that system. AWS Nitro enclaves does not make that same promise, because the entity that is attesting to you and providing you the information that allows you to trust the enclave is the same entity that runs the system. So AWS Nitro enclaves are not going to make you be able to load data into AWS if you don't trust AWS. That's a very important distinction, and AWS doesn't claim that it does. Generally, the point is your ability to tell your customers or the providers of data to you that you have no access to the data. It's a different trust relationship, and it needs to be. I just want to put that clearly out front. Another platform that we support, although it's currently not on our main tree, is the SCL4 microkernel. It's a formally verified microkernel. It's developed in Australia, I'm pretty sure, and it's got great high performance. And it's currently part of another project inside ARM Research that's going to be open source soon. This is not an area that I know a lot about, but it is. My colleague Nick is the one that has been developing this. So how did we establish transport security with an ephemeral enclave? That's the big question, because when you saw those red lines on that diagram, how do we know what we can trust? And we use that. There's a couple of techniques we use. So first, each client has an identity certificate and a key pair. That identity certificate is recorded in the policy. The client provides that certificate during the TLS handshake. That makes The enclave sure of who it's communicating with. At boot time, the enclave generates a random key pair and a self-signed certificate. And the policy, the other part, it contains one and only one supported cipher suite. The TLS server running inside the enclave is configured only with that cipher suite. So if we want to change the cipher suite, we do have to do an offline renegotiation of the policy. But how do the clients themselves establish trust in the enclave and the self-signed certificate from the enclave? And for that, we use attestation, which I gave a really brief thing at the beginning about, but essentially a way to establish trust in the state and identity of a computer. So based on a previously established trust relationship with the owner or the manufacturer of that computer. It can be the silicon vendor, Intel SGX in that case, or the cloud provider in the AWS situation. It typically relies on asymmetric cryptography, ECDSA or RSA, but please don't use RSA. In the case of SGX, it uses something referred to as EPID or EPID. I've heard it used in both terms. It has some of the same, it is an asymmetric algorithm, but it does have additional privacy features to it. That being said, it's also much more complicated, the protocol. And there's a lot of different protocols that are used. TPMs have their own protocol. Intel SGX has their own attestation protocol. ARM has created the platform security architecture attestation token and protocol. And then AWS Nitro Enclaves provide their own unique protocol. Again, everybody does it slightly differently. So on a brief overview of sort of the platonic ideal of how we're using attestation in Veracruz. Just a sec, I gotta make sure I can see this. Okay, so note on the right that the Veracruz software has randomly generated an asymmetric key pair and a self-signed certificate. The confidentiality of the private key is maintained by whichever technology is providing the enclave. You don't trust SGX, then you're not going to be able to ensure the safety of this. And to be clear up front, there has been a number of exploits on SGX in the last, it kind of comes in a steady stream these days. So it begins with the client issuing a challenge to the target system. This challenge is a large random number, in our case is 128-bit. This allows the client to ensure the freshness of the token that's being generated for it, which protects them from a message replay attack. Once the challenge is received, the target system constructs a token by calculating the cryptographic hash of various pieces of software and the configuration in the root of trust. In this example, they consist of the platform firmware, trusted OS, and the application. Additional information may also be included in the token. In our case, we place a hash of the self-signed certificate in that area. Then the token is signed with the device private key and then returned to the client, which then forwards it to the attestation service, which verifies the signature on the token with the device public key. It may additionally additionally decode some of the information in the token and provide that back to the client, and it provides a pass-fail grade. And often, like for an SGX situation, this returns also the firmware version and the update status of it. The client then verifies the challenge to make sure that it is what they sent, so they know that they're not getting a replay. And then it checks the measurement of the software to determine that it received in the token, to determine if it's what it trusts. Now the client has established trust in the token. It has also established trust in the hash that was in the token, the self-signed certificate, which it then adds to a local store of trusted certificate hashes. This means that the client software will recognize connections to servers that present and authenticate themselves with that certificate as trusted. Next, you just see the TLS client hello. The client certificate gets sent across to the server. The server responds and provides the TLS server hello, presents its certificate. The client authenticates that certificate using the value that we just stored. At that point, you have a TLS channel. However, there's a few hitches here. And now this gets into what we refer to as hybrid proxy attestation. So this platonic ideal of an attestation process, it looks great. But what if you've got two different platforms with two different attestation services, or three? Now, the client software needs to maintain support for multiple protocols, maintain trust relationships and credentials with the multiple attestation services, and must maintain a policy on which configurations to trust for each of the different platforms. Now, if we add in more client instances, then each of which must maintain a consistent policy about which configurations the platforms to trust, it starts to look a little messy. So in the nature of all software, we decided to add another attestation service. And this one, hopefully, to rule them all. This places all of the complexity for supporting multiple platforms in one place using one set of credentials for each of the services. And provides one place to maintain the policy. So what does this look like? It looks similar to before, but we've added a new app inside the enclave. Wait, I just went a bit too fast. Sorry. Called the root app on the target system. When it boots, the root app generates a public-private key pair, referred to here as the proxy public-private key pair. And the process starts with what we now refer to as native attestation, and the proxy service initiates it by issuing the challenge, same as before, receiving a token, very similar to before, except instead of the hash of the certificate, it now contains the proxy public key. And then the challenge gets put back, the signature. The token is returned to the proxy attestation service. It does the native attestation service check, receiving the result, and then it stores the proxy public key in a local database. Now, when the client wants to do the attestation, note that now we have an application, which is the Veracruz application at this point. We've got our self-signed certificate and the randomly generated key pair from the previous discussion. The client issues a challenge as before. The token is generated the same as before, except that this time, instead of being signed by the device private key, it is signed by the proxy private key and then returned to the client. Instead of the client now contacting the native attestation service, the client talks to the proxy attestation service, which verifies the token using the proxy public key and then gets the pass-fail. Everything else is as before. So that's the attestation. Now we get to the WebAssembly, which if you're a WebAssembly head, this is the part that you care, or probably we're hoping for. So anyway, WebAssembly, if you're not familiar with, which is abbreviated WASM. It's a binary instruction format for a stack-based virtual machine. It's designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. I stole this from webassembly.org. It's primarily, or I guess not primarily, but it was originally intended as a replacement for JavaScript on web clients for performance-critical applications. But there's been a lot of great research and work in this area to use it server side because it's got fantastic sandboxing features. It's agnostic to the programming language used. So you can program, I don't know all the whole list, but we use Rust. We compile it to WebAssembly. We haven't had any issues on that. If you've got an LLVM compiler for your language, you've got a target for WebAssembly. It's got platform-independent execution. Its system interaction is controlled by the WASM runtime, and it's highly portable. So why do we use WASM? The first problem that came up was that when we started on SGX, SGX doesn't let you easily load software after the enclave has already started. So unless you want to futz around with writable or executable page flags, which can get sketchy really quick, the entire program has to be known when the enclave starts. This prevents runtime loading of an encrypted program, which is one of our goals. The second problem was that we wanted to protect the enclave environment itself from uninspectable, possibly malicious programs loaded at runtime. We don't know anything about this program except a hash value. So this is where the sandboxing of WebAssembly is helpful. And additionally, right now our supported enclaves run on x86 64 and AArch 64. So the portability enclave program was a desirable feature as well. So on Veracruz, we originally started with WASM running on a formally proven custom virtual machine. But this had poor performance and was time-consuming to develop. It had a lot of really interesting features because of the formally proven nature of it, but it ended up we eventually transitioned to using the WASMI interpreter. It's written in Rust. The point, I guess the main thing here is interpreters tend to be simpler than just-in-time compilers. That's the first question. Why didn't you use a just-in-time compiler? And this reduces the size of the trusted computing base inside the enclave, but it's slow. So for JIT, a just-in-time compiler, we have it available for SEL4, but not the other platforms. So it's been a slow burn desire on our part with some work, Dominic and Shale putting the work in for that, on getting a JIT implemented for the other platforms. So the challenge on that is our SGX environment uses Rustlang's no standard, which has made this difficult. On Trustzone, we've got a limit of about 22 megabytes, so that also makes it difficult because JITs also are very, they take a lot of space, take a lot of RAM. And on AWS Nitro enclaves, honestly, this looks like the most promising one because the memory restrictions are are basically not there. And the other part is you've got a fairly rich computing environment in there. That being said, we're still hopefully maybe tomorrow, Monday, it's Sunday for me. Tomorrow, Monday, hopefully I get this merged into the main tree, and then we'll probably get some more work on Nitro enclaves from the other people on the team. So for our interface, for the programming interface, for the WebAssembly program to access the data and write the results, we're using the WASI interface, which is the WebAssembly system interface. It's a POSIX-like standard for WASM programs to interact with the system. So we're currently implementing a limited WASI layer for programs to interact with the data sources. It's primarily limited to the file interface, but in this case, the file system is an ephemeral RAM instead of a long-term file storage, inside the enclave. We've talked about architectures where we could swap out the enclave RAM to non-enclave RAM, of course, encrypted and authenticated, or even to the non-enclave file system. But we haven't gotten to that point, partially because we're not sure of the use cases, and we actually want to get more feedback from other parties on it before we dedicate the work there. The other part is we only really have about 2 to 3 people that are on this project full-time. The others are about half-time or less. So we do have a manpower crunch a little bit. So for future work, I'd say we want your help. So we're available on GitHub, and we've got a number of issues on the GitHub, and we've got them even marked as good starting places with good first issue. We are still in the process of gaining community around us. We did have our first non-ARM pull request at the beginning of last week. We hope to get more. So if you're interested in this, please hit me up, and please just take a look at our GitHub. Additional future work. If you've any experience with Project Oak or any other projects, they have a more dynamic policy system. Our policy files are very static. They're just a JSON file, and there's not really a great way for our users to negotiate them. These are so we might want to we have a desire to make them more dynamic to increase the applicability. Also, we want to support streaming computations. We've a lot of the use cases that we've talked to people about have been involved video processing, which of course we need streaming for this. Also, we want multi-TEE, multi-isolate use cases. So think of it as a privacy-preserving grid compute, or even basically a serverless. It might look like a serverless environment. We would also like dynamic checking of the runtime behavior of the program, because as it stands, the policy negotiation involves a hash of the program being run. The data providers may want certain assurances beyond just the identity of the program. They may not be able to see the program, and we may want to provide additional assurances to that. So we're batting around a couple ideas on that. Also, a lot of the use cases that we see or that we can imagine involve an external database, gigantic data sets that aren't going to fit in RAM and that aren't going to be wanted to be transmitted across the network in mass. And the challenge here is we haven't found any way to communicate with an external database without allowing a side channel of communication. So consider the case where the program provider and the database provider are colluding. The program provider could write the program so that it sends queries to the database based on the input data, and thereby bleeds the information out. So we've got a lot of questions and a lot of ideas on the database problem, but we haven't solved this yet. We're also working with a few collaborators on real-world use cases, but we're always looking for more. So if this piques your interest and this is something that you want to talk to us about, we're all ears. I'm listening. So thank you for your time, and I'm ready to take questions.
Thank you, Derek. That talk well beyond my capabilities, but fascinating nonetheless. We are right to take questions from the audience, but so far I'm told at the moment there's not a heap of questions. I do have some, though.
Okay.
I'm a little hesitant with this because it is going to show my ignorance, but let's go with it anyway. You briefly said during talking about attestation that you can use ECDSA or RSA, but please don't use RSA. And I thought RSA had variable key sizes, making it possibly suitable. So why was RSA not good in that attestation setting?
There's been some movement away from RSA recently. You'll notice that TLS 1.3 no longer supports RSA. There's also been some rumblings about from the NSA on it, although it goes in both ways. And can you trust the NSA? I think the primary reason is that RSA is very weak when it comes to very weak to quantum computation algorithms, and that's where the reticence about RSA comes from. In the case where, if you, depending on who you listen to, practical quantum computers are available within the next 10 years. And if you've got data that you want to protect for more than the next 10 years, RSA is not a great choice on that. Now,
that's not where people are hedging their bets. Yeah.
It's a hedge, but at the same time, it's a little bit of dangerous situation because there are reasons why elliptic curves are a little dangerous sometimes. NIST's recent backing off of the transition to elliptic curves gives some people pause. I don't really have a pause on that one because I think the reason they were doing it was also because of the quantum computers that may be coming about.
Cool.
But there's no consensus on exactly what there's no broad consensus on what's going on there. So
fair enough. I do have another question. When you were talking about future work, you mentioned how you would like to get some more assurances around the program. I was wondering, just speculating in my head, is an example of that where you might want to be able to say something about whether that computational workload will finish in a reasonable time? Is that an example of that kind of assurance you want?
That could be. That wasn't one that we've been thinking about in general, because in general, what the owner of the system can do is just shut it off anytime they want. So that's not necessarily a concern on the host side. What we generally think about on that is, let's consider I've got a malicious program that is just taking the input data and throwing it out on the output. It's obviously not protecting the data in any way from the receiver of the result. And so if we could provide assurances about the nature of the program so that we can say, well, for example, it only is able to do a very simple one, which is possible, is saying, well, the output size is limited to this. So then you know that your input data of, let's say the input data is 20 megabytes and the output size is 4 bytes. You know that it's not going to bleed all of your data. There's just not enough room. That's a very simple situation. But if you also consider the situation, the idea of basically, let's say, another way you might say is, let's say it's a sorting algorithm and the output data is the same size. You can formally prove a sorting algorithm. Might be something like that, but mostly when I think about it, I think about, you could also provide like a profile of the program and say, okay, this program looks like it's a sorting algorithm because we know what sorting algorithms look like. However, that's going to end up being very gameable by the writer of the program. And if they know that you're doing that check, there's a lot of ways around that. One idea that I'm particularly interested in is zero knowledge proofs, but zero knowledge proofs of knowledge have some of the same limitations of homomorphic encryption in that you basically require you turn the program itself into a circuit, which is very basically it's a logic tree, and that is very limiting as far as like loops have to be unrolled, and it can get really large and really painful extremely quickly. So my dream would be zero knowledge proof of knowledge, but I'm not sure that that's practical. But anyway, we still need to look at that.
Yeah, this would be like fascinating to keep talking about, but I'm just not going to be able to keep up with you at all on this. So maybe we should move the conversation over to the post Q&A chat session. We'll get Derek to head over that way pretty shortly. We are going to finish up here now, and we do have a